diffusivities.
Yeah.
All these things we haven't set some in the initial model. So I'm really thinking whether we need it.
Diffusivity.
Yeah, we just got the thickness diffusivity before the every model one, and that's the only diffusivity we have.
Okay. So we'll have to think about what you want there. Why do you think thickness diffusivity is important? Okay. Yeah.
Because
For everyone
got
online, we're just going to wait a couple more minutes.
variability things, and that kind of thing give us the gradient of the temperature and salinity. So we got confidence to say it may have some effect. If we haven't checked this, we couldn't see whether it is important or not.
Yeah, that's true. But it's important to think about what thickness diffusivity represents. For everyone online just joining, we're just going to wait a couple more minutes and then we'll get going. Yeah, I also don't know why do we need to have thickness diffusivity? That's it. That close? Yeah. Oh. Yes. Okay, thanks everyone online and here in person. My name is Kieran Murphy. I'm the IMAS ACEAS seminar series coordinator. Delighted to have Rio with us today. But first of all, I'd just like to, on behalf of UTAS, acknowledge all of the countries that are participating in the meeting today and to pay our respects to their elders and their ancestors and the legacy they've left us. So I'm going to hand it over to Helen for the introduction. Thank you.
So it's my pleasure to introduce Rio Furue, who's a senior researcher from Damstec, and I think this is the fourth visit that Rio has had to IMAS. And the first one was soon after 2010, when we first met when I joined an NSF proposal that Rio and Jay McCrew had put together to bring in some observations to the theoretical and numerical work that they were doing. And since then, we've continued to work together. We've had students involved in projects. We've had 6 joint publications, I think, in an ARC project. And I'm really excited to have Rio here to talk more about future work. So I think I will just hand over to Rio and let him tell you all about this new work. Rio's already given one seminar to the Furue group last week, and there's another one coming up on the 26th of March, which is an Oceans and Cryosphere seminar. So hopefully many of you will be able to come to that. That one will be about the Holloway undercurrent on Australia's northwest shelf, and a deep wave that travels from the northwest shelf around southern Australia and up as far into the East Australia. More interesting work. I'll hand over to Rio.
Thank you, Helen. So here's my talk, and I chose the word chaotic to be catchy, and a more boring term would be intrinsic variability. So I don't know if you are familiar with chaos and deterministic chaos. So I'll give kind of an extended introduction to chaos in physical oceanography. And so here's the problem. So our system obeys an equation like this or that, so which says that if you know the present state, you can calculate the future state according to this discrete equation or this differential equation. But anyway, the initial condition determines everything. That's the determinism. But for some systems, ever slight variation in the initial condition exponentially grows to become appreciable. Such a system is called chaotic. And when that happens, the system is still in principle predictable, but in practice, it's not 100% predictable. So in this case, we have to treat the system as if it were a probabilistic system. So that's a deterministic chaos. So this is a well-known example. So this is a picture from the Japan Bureau of Meteorology explaining how typhoon forecast is made. So they have a good numerical model, and then they initialize the state with an observed and estimated typhoon. And then they run a simulation once, and then they get one trajectory of typhoon. And then they slightly change the initial condition and repeat the experiment, and then get a different trajectory. So this is the trajectory of typhoon is chaotic. So it's very slight disturbance in the initial condition quickly diverges, gives a very big difference. So in this case, again, this is chaos. So, and this is not because the model is bad. Even if the model were perfect, this will happen. So if you have a better observation, then this spread will be reduced. But the keyword here is exponential growth. So as you integrate the system, the trajectory will inevitably diverge because of the chaos. Therefore, your prediction forecast has to be probabilistic. Okay, so what about the ocean? And so here's an argument about this has an implication on observations. So so this is an example of observed picture. So this is the eastern equatorial Pacific, and this is latitude, and this is depth from the surface to 1,500 meters. And then this is the equator, and this is 18 degrees north. What we are looking at is the zonal velocity and mean zonal velocity, and measured by ADCP. A lot of ADCP sections are compiled. And this is also from an observation. And in this case, it's from Argo. And this is hydrographic geostrophic calculation. But instead of using a reference of no motion, the author, Cravat et al., used the parking depth velocity as a reference of their geostrophic calculation. So, and then gets this nice set of zonal jets. And then if you compare these two, they agree very well. Even the positions of the jets agree between these two independent set of observations. So these features are real. Okay. And then I looked at those jets in our high resolution numerical model, which is called OFES. And in this set of runs, we have 10 realizations, meaning we initialize the model with a very, very slightly different initial condition and run the model 10 times. And initially, you can't distinguish those 10 runs, but eventually, in 5 to 10 years, the trajectory of the ocean spreads. And so that's how I got this picture. So the horizontal axis is time from 65 to 15. And then vertical axis is latitude. Here's the equator. And I look at a particular depth and pick up eastward velocity and then determine its core, so the position of the jet. And then I plot a point there if I find the eastward jet there. And I did that for the 10 runs. And if you look at this particular jet near the equator, which is this one, the position is quite coherent, meaning all 10 members agree about the position of the jet. But if we go higher latitude, the positions differ between runs. That means the positions of these jets are not perfectly deterministic. They differ from run to run. So the position of these jets. And so this is, we need to know, because suppose as a thought experiment, suppose you found a current ocean current at a particular position several years ago. Then you came back to the same position and measured and found the current was shifted by 100 kilometers or 200 kilometers. Then you ask why, and you hypothesize perhaps forcing of the current has changed over the years. That's possible. Also, this particular current is maybe migrating like a wave over the years. Or the position is just random, could be random. If that's the case, it's futile to look for explanations because the position is determined by some chance. Okay, and so this is a probabilistic view of reality. So the reality is just one realization of many possibilities. The reality doesn't have to be what it is. So that's the probabilistic view of our system. And so there is a danger here. So you have a numerical model and you compare the numerical model with an observation. But the question is, should the flow field of your model have to agree with observation? Or is all disagreement due to the model defect or error in observations? Not necessarily. Even a perfect model would disagree with the reality if the system is chaotic. So that's the message I want to actually convey. That's why that's the reason for this extended introduction. So we have been looking at probabilistic properties of the ocean currents, our group. So these two papers are about the meander of the crochet extension, and it's probabilistic. And after 10 years or 20 years, the trajectory of crochet extension differs between ensemble members on annual average. So it has a long time scale. And this is a probabilistic view of the Crochet large meander. So the Crochet takes two paths. Sometimes it takes a straight path. Sometimes it has a large meander. It's a bistable system. But the transition is actually probabilistic. It's not deterministic. So there's a paper like that. And as I said, I looked at the zonal jets, the probabilistic properties of the zonal jets. Now, so this is main subject of today's talk, which is Indonesian Throughflow. So this is a picture taken from Min Fen's review paper. And then, of course, we know that the transport, the annual mean transport of the ITF is mainly determined by the severe drop dynamics, largely determined by it. And there is an argument that if you increase vertical diffusion everywhere, the transport of the ITF increases. And there is some reason for it, but here's an interesting point. So our group did this study comparing high resolution numerical model with and without tidal mixing parameterization. And then this is the horizontal axis, which is time from 60s to 2015. And then vertical axis, this black curve, is the difference in the ITF transport between the two runs, sensitivity run and the control run. As you can see, the ITF transport increases, gradually increases by the end of this integration, it's like one severe drop. But the question is, was this increase actually due to vertical mixing? Or is there any probabilistic component to it? That's the question I ask. And so let's go back to the issue of chaos. So here's a thought experiment. So you increase vertical mixing for just one day, and then revert the values to the original value, and then continue the integration for 50 years. And this will kick the system into a different trajectory. So like changing the initial condition, changing parameters will act as a disturbance. So the change you see here could be due to just chaos. This may not be due to vertical mixing. So that's a danger. Therefore, we have to know the probabilistic properties of the Indonesian throughflow to make sure this is not chaos. Okay, so this is my data. So the model is called OFS version 2. And it's 1/10 of a degree resolution, and the domain is semi-global. And it has a high vertical resolution, and it's forced by this atmospheric reanalysis product. And the length of the integration is like 50 years or 60 years. And we have, as I said, 10 members. And I use monthly averages, but basically what I'm going to show are annual averages. And I calculate transports across the channels, and also I calculate barotropic stream functions. And okay, so here are my sections to calculate transports. So here's section 1, 2, 3, 4. And on the Pacific side, I have these 6 sections. And I calculate barotropic transport. And okay, so before going into the result, I want to make sure that there's little leak in volume. So this is a difference. Horizontal axis is time. This is the difference between the outflow into the Indian Ocean and the inflow into the Indonesian Seas. And the difference is small compared to what I'm going to talk about. It's at most 0.07 severe drops. And then this error must be due to the fact that I ignored sea level variability. And okay, so this is the main plot. So this is time axis again. And this is the total ITF transport on the Indian side. And okay, so this is like 13 severe drops. And as you know, this red curve is the Nino 3.4 index anomaly, again, annual mean. So as you know, the Indonesian throughflow is stronger when La Nina happens, like this. And then the interesting point is that the Indonesian throughflow transports can be differ by 1 severe drop between ensemble members. So this is the chaotic component, which is intrinsic variability, which is not controlled by external forcing. This is a random component of the Indonesian throughflow transport. So this is the ensemble anomaly. So this is a difference between each individual transport and the average over 10 members. So the standard deviation is not large. It's like 0.2 to 0.3 severe drops. But sometimes the member with largest transport and the member with smallest transport and the transport can be differ more than 1 severe drop. So this is a table showing the 5 topmost years with large difference between large member and small member. Okay. And this is the probably picture you know very well. So on this is a breakdown of the transport. The on-by channel dominates the Indonesian through transport. And then on the Pacific side, this channel, I don't know its name, but this channel dominates the transport. And then the variation between members is large also in these channels. So from now on, I focus on only this channel and that channel. And this is a vertical profiles for all the members of the ensemble anomaly. And this is on the Indian side, and this is the Pacific side for all members. And let's look at this one first. As you can see, the surface variability is mess for surface top 300 meters. And even below that, it's a kind of mess. But if you look at the Indian side, the vertical profile is has a kind of a structure there. And okay. I did an EOF, calculated EOF modes using all members and all years, as if all years are independent from each other. And I forgot to tell you that there is very little temporal self autocorrelation. So I thought, okay, let's treat each year as an independent random data. So, and did EOF. So you calculate the vertical profile of each EOF mode. And then on the Indian side, the EOF1 has a variability of 67%. No. On the Pacific side, on the other hand, even EOF1 has only 30% of variability. And there is very little barotropic transport. In contrast, this mode has a clear barotropic transport. So this mode must be associated with the change in the barotropic in ITF transport. Let's skip this, let's skip that. So now I'd like to extract the component that is correlated with the ITF transport. So this is a vertical profile, which is a function of depth, time, and member number. And it's a linearly related to the ITF transport, which is a function of time and member. And this coefficient is the function of Z. And this is a residual. So this is linear regression. And later I will show a linear regression of the barotropic stream function, which is a function of longitude, latitude, time, and member number, which is decomposed into the spatial pattern and the ITF transport anomaly. Okay, so here is the linear regression of the vertical profile, and I'm plotting alpha times ITF. So this is a component of this vertical profile, which is related to the ITF transport for a particular member for a particular year. So this one has the largest transport among the 10 members. And then this is the year with the largest difference between the members. And this purple curve is the actual transport anomaly. And this green curve is a linear regression times ITF transport. So as you can see, this green profile explains a lot of this actual anomaly. And then this is a member with the minimal, smallest ITF transport, and the same story. It's explained by this linear regression. And on the other hand, this is the Pacific side. And this is a linear regression for the same members. And in this case, there is clear barotropic transport. So this is a profile associated with in ITF anomaly. And on the other hand, the actual profile is much noisier than on the Indian side. So that's basically this. So on the Pacific side, there's a lot of chaotic variability, which is not related to the ITF variability. But on the Indian side, so if you look at the EOF pattern, which is very similar to this linear regression with two humps. So on the Indian side, the dominant intrinsic variability is that associated with ITF variability. Okay. Now, so you might think that this kind of a variability is just a noise. And it's true that eddies and the nonlinear meandering is chaotic. So you would expect that this is just a local meandering or eddies, but that's not the case. That's the interesting point here. So this is the member in year 1986 with the largest transport. And this, we are now looking at the anomalous barotropic stream function. So because this is a barotropic stream function, the velocity or transport is proportional to its gradient. So what you can say from this is that the westward transport is increased by 0.5 sphere drops. And then it turns southward in the Makassar Strait. Then it flows like that. So this is just a basic pattern of the ITF. So this anomaly is not a local phenomenon. It's just a genuine increase in the ITF transport. And the same story is here. This is a member with the smallest transport of that in that particular year. So the transport is decreased with the same pattern. And then the lower panels show the linear regression. And it's the same story. So the bottom line is the ITF itself is increased by or decreased somehow under the same wind stress, same everything. And then this is what happens. So I look at this particular panel, but for the global ocean. The same plot, but for the global ocean. So this is a barotropic stream function anomaly. So you can draw arrows of transport. And then you can see that the southward transport is increased, and then the north equatorial current is increased, and it bumps into Africa and flows southward in the western boundary current, and the bend westward into the Atlantic. And also there is that's 0.5 severe drops. And then there is an increase by 0.4 severe drops of the ACC transport. And unfortunately, the regression is very noisy, so you can't tell where actually that increase happens. But the total increase is certain, which is 0.4 severe drops. So there's decrease in ACC transport. So the total anomaly of 0.9 severe drops flows into the Atlantic, and then bumps into South America and flows like that. So there's a prominent bottom topography here, and then it flows westward, and then it hits the ridge or the bottom topography to the east of New Zealand, and then 0.5 of the transport flows along the bottom cliff northward and comes back to the Indonesian Seas. And then the remaining 0.4 severe drops goes around. And then this is a simultaneous correlation. So this happens within 1 year. That means this response must be barotropic. Baroclinic response should be much slower. So the question is why? So I don't have an answer to that. I only have a hypothesis. So I thought maybe the zonal jets are maybe doing something. And if you look at this barotropic stream function, you see these stripes. They are zonal jets, quasi-barotropic zonal jets. And then this is again observation, and this is our model. And although our jets are much weaker than observed, but we do have these jets. And Okay, maybe I show this first. So here's an animation of barotropic stream function. And this is an anomaly of particular member from the ensemble average, the average over the 10 members. And then this bar means two-year running average to extract jets. And okay, so this is animation, month by month. So these barotropic jets migrate, and this feature is well known. And because these jets are chaotic, so it shows up in this ensemble anomaly. That means these stripes differ between ensemble members. Then when the year 1986 comes, which has the largest transport, you see this little but a strong anomaly in the stream function value. So I thought these jets migrate, and when it hits the Indonesian seas, which might do something to the barotropic transport. And the idea is this. Maybe I'll show this first. So this is a lagged regression. And so when the ITF is maximum, which is this 1 year before the maximum, there is a barotropic stream function, negative anomaly is here. And it comes to this Philippine Sea, this opening. And if we go back, these stripes migrate, as I show. So these jets could be, and this is a linear regression, so there is a correlation between the ITF transport and these stream function anomalies. Okay, so this is just a hypothesis. So this is a traditional view of the ITF. It's driven by Pacific winds through severe drop dynamics. But there are other sources of stress. So if we have Reynolds stress, which is the nonlinear term in the momentum equation, U times Ux or U times V of X, things like that. So that can act as stress. Also, there is J-bar impacts. So this is a correlation between bottom pressure and the bottom topography, and which acts, so you can call it form stress, bottom form stress. So bottom form stress is a stress acting on the barotropic ocean. So if those jets have bottom component, then it could exert some stress to the system, barotropic system. And there is an interesting feature here. So these are zonal jets. Then it suddenly disappears at this cliff at the bottom. So the ocean is much shallower here than that here. So this stripe stops here. So these jets must be feeling the bottom. And if so, these jets could exert some stress to the barotropic system to alter the barotropic Indonesian throughflow. So basically, maybe I spoke too fast. Probably. Basically, this is my conclusion. And I want to test this hypothesis of mine by examining these stresses in our model, but the computation is takes a lot of time and a lot of coding. So I'm procrastinating, but I want to do this calculation, but if anybody wants to do this, I invite you to do it. Okay. So this is my conclusion.
Thanks, Furue. Left lots of time for questions and discussion, which is good. anyone, maybe online, we can open the floor online for questions first. Because often we forget about people. And you got a question, I can see it, it's very neat.
But I don't want to get in the way of the other people.
If someone online would like to unmute and go ahead, maybe just put up your hand, otherwise I'll let the head tell them that. Okay. Yeah, do you want to take it away first?
Yeah. You mentioned that these zonal jets that you got from the ensemble perturbations had a somewhat barotropic structure.
Yeah.
But this is model world, so we can test that, right? You can just
Yes.
look at the structure.
Look at the structure. And so I looked at the structure. It's very deep. And sometimes it reaches the bottom. And some of these jets actually extend from the bottom upward. So
So you know that they interact with the bottom because they are full depth.
right. But I even have
To test this hypothesis, you have to calculate the stress is the right one to increase or decrease.
the idea. Yeah.
Calculate with J-bar term.
On your conclusion slide,
This one.
no,
Okay.
one with the arrows showing a
Oh, yeah,
slowing of the ACC.
That's right, that's right.
Acceleration of the throughflow.
Yep.
I'm sorry if I wasn't paying attention, but would you mind explaining what creates this anomaly field? So what's
Yeah.
an anomaly to?
Oh, okay. So this is basically the deviation from the
Mean of the 10 members. So the average over the 10 members is
presumably represent the component which is driven by external forces, determined by external forcing.
the deviation from it is not determined by the external forcing because it differs from member to member.
And was there a specific perturbation in the run that led
No.
to that? No. Okay.
No, the anomaly grows by themselves. That's why it's called intrinsic variability.
Yeah, just curious about your hypothesis. At the start, you mentioned that three hypotheses that indicate whether the jets change the positions, and one is the movement of the jets. And from that slides, we have the time over time change of the jets.
Right.
Yeah, that.
No, you mean the animation?
Animation.
Animation. Okay, so I'll put up the animation. So that yeah, they change this one. So yeah, they keep moving.
Yeah,
Very slowly.
and you have mentioned some bottom stress
Right.
around the east of Australia there, and exactly we could see some weaker jets after just across these regions, and yeah, just a bit curious. So is that what you have found that kind of clarify that is a movement of jets and
So you are asking why these jets move?
no, I mean is you have mentioned the alteration of the jet positions, right? And that is one of the reasons that the jet movement. Is that what you found? And maybe
No, I didn't find it. It's just my hypothesis. So let's move, and sometimes it hits the critical point of Indonesian throughflow.
yeah, okay.
Yeah, that's my hypothesis.
Yeah, and I got a bit curious whether the bottom stress could alter the position of the jets.
So it could alter the position by bottom stress could alter the position of the jets. Oh yes.
Yeah.
Yeah,
Yeah,
it could change the position of the jets, of course.
Yeah, that's what I found in the figure. Just check with you at the telegraph.
Right.
So very nice speaking. Yeah, about this.
everyone online is very shy. Do you mind if I'll just ask them a question? So I'm a marine ecologist, so this is slightly out of my field, so be kind. I guess from your conclusions of the anomaly that you were showing, that sort of hit the shelf along New Zealand and some diverts north, some south.
Right.
What would the implications of that be for movement of water in the Southern Ocean?
Oh, so actually, the only implication I got from that break is that it's an evidence that these zonal jets are feeling the bottom, strongly feeling the bottom. That's all. Yeah, that's the only implication.
I have a slightly provocative question on this slide.
Sure.
So my interpretation of this is that you're saying over a 2-year timescale, there is no intrinsic variability in the large-scale ocean currents because there's no imprint of the gyres or the western boundary currents or the ACC here, right? We see eddies, but that's just from moving the eddies into slightly different places. But there's no subtropical gyre in the Pacific or the Atlantic.
Oh, right. So there is very little sign of subtropical gyres.
Right.
So
So
the-
those large-scale ocean circulations are purely externally forced, and there is no intrinsic variability in their
Very
strength.
little intrinsic variability for those large scale feature. Yeah, maybe they are too powerful, subtropical gyres.
Yeah. Okay.
Yeah, but if you look carefully, like I did for the ITF, you might see some intrinsic variability in the subtropical gyre. I don't know. Maybe you need to take some different time average or something. I don't know.
Mhm.
So yeah, so this impact is not large, just 1 severe drops at most, 1 severe drop at most. But as I said, these jets are less than 1/2 of the observed. So the actual jets may be larger in reality. And if so, this intrinsic variability of the ITF may be larger. I don't know.
Okay, we've got a couple of questions online, so I'll read the first one and then you go up next. So, it's Sugata. Thanks very much for the presentation. It was great. They want to ask why on the Pacific side, mainly near Mindanao coast, 54 section, there's a high wave number which is surface intensified.
That's a very interesting question, actually. So I'm actually intrigued by this feature. So this is a Mindanao place, and then surface intensified high resolution, high frequency or high wave number variability is huge. But the strange thing is that even the linear regression has this high wave number pattern. And some of these peaks are larger than the confidence interval. So statistically, these peaks may be significant. But I'm puzzled why do we have to have this kind of a
So you're not sure what
and in the annual mean. Strange, right? So I'm intrigued, but I don't have the answer. That's a very mystery.
I hope that answers the question. So we have one in the room here. Sorry.
I guess I was going back to what was partly motivation for this was the study with the tidal parameterization. So were you able to conclude then whether that's the effect of the tidal parameterization or was that just chaos?
Right. Okay. So I have to come back. Yes. So this actually internal intrinsic variability doesn't last for a long time. As I said, it doesn't have a autocorrelation. So that means if you integrate average over 10 years, this will be gone. But if you look at this graph, this is a long, slow change. So this should be the real impact of vertical diffusion.
And we have a technical question online. Zubin asks, do you calculate the stream function via post-processing?
No. Oh, yeah, it's post-processing, yes.
Yeah, not from direct input.
No.
Okay. So it's because they're saying their previous experience with similar model setup indicated calculation via post-processing could be quite noisy.
Stream function.
Yeah. Do you want to comment online more?
Quite noisy. Why is that? Maybe, yes. So I did this quite a lot, like calculating transport. And then when you calculate transport from the model output, you have to use the same scheme as the model uses. Otherwise, there's leak in volume. But I use so this model is based on MOM. So I looked at the manual of MOM and I used the exact same discrete continuity equation to avoid that problem. So that answers the question. So I verify my calculation is correct. My volume is conserved. Yep.
Any other burning questions? I've got it. This might be a tough one to answer, but I guess my main interest in this area would be getting a lot of the outputs from Earth system models. I don't know a lot about this kind of bottom-up process or the physical processes. But are there any kind of takeaways from your findings that would help us understand Earth system model outputs like primary production and how this kind of anomaly could affect those projections that we currently have?
I don't know. I want to ask people here about that. But this particular subject may not have any implication, but chaos is everywhere in the ocean, right? So you need to know about the chaotic property when you compare with observational results. And when you interpret your observational results, you need to be always careful about is this by chance or not.
Right. It's more philosophical.
Right. Yeah. Right.
That's great. Okay. If we haven't got any more questions, I might just ask you to join me in thanking Rio again for the great talk. Thank you.
Thank you very much.